So today's lecture is going to be about lists. Well, I say it's going to be about lists. It's going to be about a lot more than just lists, but we're going to basically hang the ideas and the things we're going to learn today around the theme of programming with lists. So just a recap, where we left off last time, we talked a little bit about lists, and this is just a reminder what lists are all about. So lists are all about collections of things, and those things all have the same type, and the lists themselves can contain elements of any type, as long as all the elements have the same type. And so this slide just reminds you of various syntactic shorthands. So let's look inside lists and try and understand a bit more about how they work. So a list is really very much like the data structure that we define for a hand of cards. There are two kinds of lists, either a non-empty list or an empty list. So we can think of a list as being built from a data structure that looks a bit like this, except we have a different syntax for it, and which there are two kinds of lists, an empty and a non-empty one. But the question is, if we define it in this way, what do we put here? When we wanted to model a list of cards using a new data type, we put a card there. But lists, as we've seen them built into Haskell, are polymorphic. They can contain any kind of element. So the question is, if they can contain any kind, what do we put there? And the answer is, as you probably recall, is that we can put a parameter. We make it a parameterized, a generic type. And this is the way it looks in the Haskell style. It's a list of some type A, has the following structure. Okay. Now, Haskell's built-in lists are really just the same as this, except they have special syntax. They have special syntax because we use them a lot. And so it's very convenient to add some extra syntax to make programming with lists a little bit more convenient than it would otherwise be. But in effect, this is the, if you like, the pseudocode that represent Haskell lists, that a list is this mixfix, list type is this mixfix type. It's the sort of not infix, it's not prefix, it's a bit of both. And there's the type parameter A, and there are two kinds of things. It's either the empty list, or it's an element of type A, followed by, with this constructor cons, another list of A's. Okay, so this is more or less the way that lists are defined, except this syntax, you can't use this kind of syntax with your own user-defined types. Okay, any questions? And the remaining, yeah, sorry.
Is there no way to define syntactic sugar inside
No, Haskell doesn't have what some languages have, and that is a macro language that enables you to build syntactic sugar. But very often, Haskell's other virtues in terms of its expressiveness enables you to write rather compact representations of most things you want. So it's not something that is considered generally lacking from Haskell. But it's a good point. There is no mechanism for introducing syntactic shorthands. Okay, now let's talk about types of things involving lists. Lists themselves are polymorphic. They can have more than one type. And so functions over lists very often are also polymorphic, and we'll play around with a number of these functions shortly. For example, reversing a list, it doesn't really matter what's in the list. The procedure, the algorithm for reversing a list is the same, no matter what the list contains. Because to reverse a list, you don't need to look at the things in the list. And for that reason, reverse is a purely polymorphic function. And the same thing can be said for the append operation, which takes a list, another list, and joins them together to produce a third list. Now, in some cases, depending on the function you have, they can be polymorphic, but they can be constrained in some way. And these constraints are related to the notion of a class, which is a bit like an interface. So for example, if a function works for all types, providing that you can compare elements of that type, then you might have a constraint of this form, that it works for types A, for which there is an ordering relation defined. Another example that we've seen before is where we have a constraint requiring the use of an equality operation on the type. For example, if you wanted to find an element in some way in a list of elements, you wanted to ask whether an element is found in a given list. In order to know whether a given element is the same as one of the elements in a list, you have to be able to compare them to see whether they're equal. And so a function of that type would require that you can perform the operation on any list of things you like, providing the things have an equality operation on them. Okay? We'll see some more concrete examples of this later on. And these are the standard built-in classes that you will come across quite often, namely OR, EQ, and num for different kinds of numeric operations. Any questions about these ideas? The details will become clearer when we see more examples, but for the moment I think the concepts probably are not too unfamiliar. Okay, so what I'm going to do now is go through a bunch of standard functions. They're functions you don't need to define because they're already defined for you in the prelude, but it's instructive to look at a number of these examples for various reasons. Firstly, because they show a variety of styles of definition of recursive functions over lists. Secondly, they will enable us to think a little bit more about testing and properties towards understanding and controlling how to use quick check, which was something we will need rather soon in the course. So without further ado, I will switch over to the editor, and there's my rough plan of what I want to do. So what I want to do then is to look at some typical examples of functions defined in the prelude. And the prelude is the name for the collection of functions, the module if you like, which is imported automatically when you start when you write a Haskell program. You get a bunch of definitions for free. They're already imported for you without having to import anything, and that's called the prelude. Okay? And the prelude includes functions like, for example, reverse or append. So let's start with append, and I'm going to give the definition of append. Now, append is a function which takes a list of things and another list of things and produces a third list of the same kind formed by joining this list and this list together. Now I can't actually define append in this way because it's already defined in the prelude, and you can't shadow existing definitions in this way. So what I have to do if I want to use the same name is to hide this function when I do the import. So I can do that by importing the prelude explicitly and hiding. I'm going to hide a bunch of things, but the first thing I'm going to hide is this append function. Okay? The reason I put the second set of brackets here is because I'm going to add more things as we go along. Okay? Any questions? In fact, I can tell you the next thing I'll look at is reverse. So there are two functions that I'm going to hide from the prelude. And in fact, if I want to still use those hidden functions, I can import them again. This is a little bit not necessarily something we need, but actually now I can use the original definitions of append and reverse with the qualified name P. So let me just compile that. Lacks accompanying binding. Let me just comment that out for a second. So I've hidden the definition of append. So for example, if I try to write 1 appended to 2, it says it's not in scope. But what I can do is I can use the definition of append that I've just imported, which is called p dot append, I believe. Oh, it's not quite right. That's p. Let me try a simpler example. Maybe the syntax is not right. Just make sure I have compiled that. Let's take reverse. Oops. Let's reverse a small list, and it should say not defined, not in scope, and I should be able to do p.reverse, so I can access the original definitions via p, and I need to get my syntax right to access this infix function. I don't quite know what I was doing wrong there. I'll work that out later. Okay, so we've hidden the original definitions, so we can now happily redefine them. So let's go and do that. So here we're defining an infix function. We can define it either as a prefix function by keeping the brackets around it, or we can define it as an infix function by taking away the brackets. Let's define it as an infix function. So we're going to take this list, and we're going to take this list, and we're going to build a new list, which is just like this list followed by this list. Okay? So we're going to do this by recursion. But we have two parameters. So we're going to do recursion by traversing the first parameter or the second parameter. What do you think? The suggestion is the first. Now, lists are something which are built and accessed from the front. So for that reason, what we need to do to join these two lists together is get to the end of the first list. We need to walk down the first list until we get to the end. When we get to the end, we want to glue in the second list. So our recursion will be in the first parameter. And this is a classical recursive pattern. There will be two cases, one for the empty list and one for the non-empty list. Let's call it x, and x is y's. And let me just use consistent terminology there. Let's call that y's. Okay. All right, so here's two clauses for our definition. And we're going to say, what happens when we try and append an empty list to this guy? Well, that's an easy case. What's the answer there? It's just y's. You join an empty list on the front of some list, you get that list back again. Okay, now we're going to try and work out what this thing will be, and we're going to define it in terms of the subproblem, the smaller problem. Let's suppose you knew what the answer for this thing was. You knew what the answer for that was. How would you take that list and turn it into the answer that we want for this thing here? What's the difference between this one and this one? Well, let's write it down. Let's write an example. If I have 2, 3 appended onto 4, 5, oops, I haven't defined it yet. Okay, let's just write it out without actually typing the. If I have 2, 3 appended onto 4, 5, and I want to know what the answer to 1, 2, 3 appended onto 4, 5. If I wanted to modify this thing to give you the same answer as this thing here, what would I have to do? Well, this list is a bit like the answer I want, except I'm missing the first element. I'd have to put the first element on the front. So I'd want to put 1 on the front of that thing there. So we do the same thing here. If we want to build the answer, we build the answer by putting 1 on the front of the append of this smaller list. to y's. So what you see here is that we solve this bigger problem in terms of this solution to this smaller problem. And that's a classic case of simple recursive definition. Let's just compile that and check that it does the right sort of thing. So now we should be able to apply this to any kind of list. A string is a list. It's just a list of characters with a special syntax because we use it quite a lot. Oh. What did I do? Oh, I did plus, yes. I can't add them together because they're not numbers, but I can join them together because they are lists. Okay, any questions? All right. If you're very quiet, I assume you don't understand anything, and I'll go even more slowly. So if you want me to go a little bit faster, you'll have to be a little bit more responsive. Because I can go as slow as you like. Okay, let's reverse a list. Let's reverse a list using the same kind of pattern. Reversing the empty list. Reversing a non-empty list. Let's call it x followed by x's. You see the naming convention here. Because this is a polymorphic function, it applies to any type of thing. So it doesn't make sense to give it a long and fancy name, because it could be anything. It could be a bool, it could be an int. So typically when we're talking about the elements, we use a singular, and when we're talking about a list of those elements, we'll use a plural, put an s on the end. Okay, so that's a standard naming convention you'll see with polymorphic definitions. Okay, the question is then, how do we find the answer to this thing if we know what the answer to this thing is? So we want to reverse a big list, and we know how to reverse what the answer is for a smaller list. What would we do with that front element? Yeah. We'd append the x in the end, okay? So what about that? Does that look good? A list, that's right. Remember, append takes a list on one side and a list on the other. So we can't append a single element. That's the wrong type. It has to be the same type as the thing on the other side, and it has to be a list. So we make a small list out of it, and that's that one there. Okay? So now we should be able to reverse the list from 1 to 10, and indeed it does what you would expect. And in fact, you could also do a quick check to check that our definition of reverse is the same, gives the same answer as the built-in one. Now it turns out that this definition of reverse is actually not a very good definition of reverse. It's not very good because it has bad complexity. So why does it have bad complexity? Well, to understand that, we have to understand what is the cost of appending two lists together. Well, because we only have access to a list from the front of the list, in order to get to the very end of the list, in order to join two lists together, we have to walk down the list. As we go along, we spit out new values for the new list. Okay? So in order to append a list A to a list B, the number of computation steps we need is roughly the size of A, because we have to traverse A. So now we have a definition of reverse, which in each computation step has to append. So in each computation step, you have to do an append operation. And each append operation, the cost of it will be proportional to the size of that list. So that means in the first recursive call, if you have a list of length n, this is something like n minus 1. So it's n minus 1 operations for the first append, n minus 2 operations for the second append, n minus 3 for the third append, and so on. So what is the sum of all those operations? What does it cost? The sum of n, n minus 1, n minus 2, and so on, roughly. Yeah, it's roughly n squared, let's say. Okay, asymptotically, order n squared. So we have a reverse operation which is quadratic time. And that's not very efficient. Okay? And the reason is because we're doing reverse by doing repeated append. Okay? So how would we actually define this so that it's not so inefficient? Well, A typical way to do it would be to use what's called an accumulating parameter. Problem with reversing in this way is that we need to basically, to avoid this extra cost, we need to avoid doing this append operation on each step. So the classic way of solving this kind of problem is to use a helper function. So let's suppose we call this function rev, and I'm going to use a helper function. Well, I'm going to call it here rev into, reverse into. I'm going to add an extra parameter to this reverse into function. And this is going to be called the accumulating parameter. So the idea is that you have a helper function which has an extra parameter, and this extra parameter I'm going to use as I go along to build up the result that I'm interested in. So this parameter will hold the result so far. Okay? And when we begin, the result so far is nothing. We haven't got any elements yet. So what we're going to do is step by step transfer the elements from this list into this list, building up the reversed list as we go along. Once this gets down to the empty list, we're done, and the answer will be whatever is in this accumulated parameter. Okay? So that's the accumulator. Let's call it A. Once we got the empty list, the answer will be just A. I could use the same names, X and X's, but I'll change the names so you don't get confused. So if I want to reverse into this list here, and I have this guy here, well, what I need to do is I need to now put this first element on the front of this accumulated argument. So I put Y on the front of A, and I continue with A's. Okay, this may seem a little bit mystical at the moment, because it's a slightly different form of recursion. I haven't defined the thing directly, I've defined it indirectly, and you can think of this as a bit more like a kind of a typical imperative program, where these are the parameters are like the state variables, and we're taking this state variable and we're modifying it on each iteration of the loop. So each iteration of the loop we add another element from the front of the list, and then we add another element on front of that. Okay. And rev will indeed do the same as you would expect. Sorry. Okay. So to see how this works, really you have to see that when you start off, if I want to reverse the list 1, 2, for example, what Haskell will do is say, how do I do that? Well, it'll look at the definition. The definition says reversing 1, 2, oh, that's the same as, so it will rewrite that into this thing here, rev into empty 1, 2, and then it will say, well, what do I do with that thing? How do I compute this thing? It'll look at the definition and say, well, is the second argument empty? No, it isn't. So this equation is no good. But this equation is good. So what that will tell us is that rev into of that thing will be equal to this thing here, rev into, where we'll put the first element on the front of the accumulating parameter. We'll put the first element, which is 1, on the front of the accumulating parameter, which is here the empty list. In other words, it'll be 1. And the second argument will be the rest. And then it will do another step. Doing the same thing, it will put the first element 2 on the front of the accumulating parameter, giving us 2, 1, and the empty list. And then finally, when you have the empty list, the answer will be whatever's been accumulated in the accumulating parameter, namely 2 and 1. Okay. Now I can't type return here and do anything sensible because you can't do a chain of equalities. When you test for equality between two things, the result is a Boolean. And a Boolean cannot be compared for equality with something which is not a Boolean. So I can't actually press the return here and get it to say true. I'd have to write it in a different way.